In this video, I'm going to be talking about Emmy Noether and Noether's theorem. Emmy Noether was one of the most influential mathematicians in all of the 20th century, but few people have heard her name. I'm going to tell you a little bit about her life and her work, and then we're going to spend some time discussing her theorem that relates continuous symmetries to conserved quantities in physical systems. Emmy Noether was born in 1882 in Erlangen, Germany. She wanted to study mathematics, but at the time, women were only allowed to audit classes. So in the winter of 1903-1904, she audited classes taught by mathematicians such as David Hilbert, Felix Klein, and Hermann Minkowski at the University of Göttingen. She returned to Erlangen and was finally able to study mathematics there and received her PhD in 1907 with a dissertation on algebraic invariance. In 1915, David Hilbert and Felix Klein invited her to Göttingen to help them work on some of the mathematics behind the theory of general relativity. She eventually decided to maintain there, but the rest of the faculty were not okay with having a woman teach at the university. So she was only allowed to lecture in classes when they had Hilbert's name officially on the transcript. In 1918, she came up with her famous theory in theoretical physics. A copy of this is shown here. Beyond theoretical physics, she was very interested in a lot of different types of algebra and was an absolutely extraordinary mathematician. In 1920, she published concerning moduli in non-commutative fields, particularly in differential and difference terms, in Mathematische Zeitschrift. This was a phenomenal paper and made the mathematics community take note of her main achievements. So throughout the rest of her career, she studied non-commutative algebras, edited the Mathematische Annalen, which is an incredibly important journal, and was part of the most exciting mathematical research going on in Göttingen. Then in 1933, the Nazis came to power in Germany, and Noether and many of the other Jewish professors at Göttingen were dismissed, and she, as a pacifist, did not feel that she could be safe in Germany, so she accepted a post as a visiting professor of math at Bryn Mawr College and lectured and continued her research there and at the Institute for Advanced Study in Princeton. She died in 1935 following complications after an operation for an ovarian cyst. Sadly, the extent of her influence in mathematics cannot ever be accurately known, for much of her work appeared in publications of students and colleagues, most of whom had male names. Sometimes they would mention that she offered insight or was there to help complete some idea, but none truly gave her the credit that she really deserved. We're going to spend the rest of this video on Noether's theorem. Noether's theorem states every continuous or differentiable symmetry of the action has a corresponding conserved quantity. This is our action S is the integral from t1 to t2 of the Lagrangian of coordinates q, q dot, and t integrated dt. Let's consider some change in coordinates. So we have SI's, which are a function of zeta for each of the QI's. Then the action has a continuous symmetry if the Lagrangian at S prime, and t is equal to the Lagrangian at q prime, and t for all values of zeta. This is our definition of a continuous symmetry. This quantity here, C, is the sum on I of dl by dsi dot dsi by d zeta. This is the definition of the conserved quantity. This is Noether's theorem, and we're going to spend a little while discussing it and some of its implications. Let's think about these conserved quantities. What do they mean? Imagine I have one of these continuous symmetries. I've got a Lagrangian that depends on my initial coordinates q and q dot, and I've got another Lagrangian that depends on these components s of zeta, s dot of zeta. These two Lagrangians are equal for all values of zeta. Let's imagine we have some path, gamma 1, and this path, gamma 1, is the path that minimizes the action in the variables q. Here's another path, this is gamma 2, and this minimizes the action for the variable s. If I were to expand s for small values of zeta, I would say that the difference between these would be, I guess, at the starting point, p1 times delta zeta, and at the ending point, p2 times delta zeta. So the action of gamma 2, this path here, s of gamma 2 is equal to s of gamma 1 plus ds d zeta times delta zeta. Basically, that is the area enclosed by this little rectangle. Since we know that these two Lagrangians are equal for all values of zeta, we know that the action gamma 2 must be equal to the action at gamma 1. Therefore, ds by d zeta here is equal to 0. This is equivalent to saying that the derivative of the Lagrangian with respect to zeta is 0. Let's expand this term here. ds by d zeta, we know it equals 0, so let's expand this out. So we get dl by ds, ds by d zeta, plus dl by ds prime by d zeta. Based on our definition of the Euler-Lagrange equations, we can replace this term here with d by dt of dl by ds dot. Let's recombine these terms. So really, we're undoing the chain rule here. So here we've got d by dt acting on dl by ds dot, and here we've got d by dt acting on ds dot by d zeta. So let's undo the chain rule, and we end up with d by dt, dl by ds dot, ds by d zeta, and that's equal to 0. So since this is a total derivative equal to 0, we can integrate it, and we end up with our conserved quantity here being dl by ds dot, ds by d zeta is equal to our conserved quantity. So this is how we would derive what quantity is conserved. Let's have a look at some examples that we sort of take for granted in classical mechanics. Imagine we have a continuous translational symmetry, which we do, for instance, a 2D system with gravity. It doesn't matter where I pick the origin of my coordinate system. I can pick it at x is equal to 0 or at x is equal to a, and either one are completely interchangeable. In this case, y does not have this symmetry. So if I were to write down my Lagrangian here, I have L is equal to 1/2 m times x dot squared plus y dot squared minus mg y. And this happens whether or not I have my x as an x plus a or a regular x. I'm going to get the same kinetic energy. Here, if I were to substitute y goes to y plus a, I would end up with a different Lagrangian here. My conserved quantity, the sum on my different coordinates of dl by d coordinate dot d coordinate by dA. So I do this for both x and y. The y term vanishes because it does not depend on a. And I end up with my first term here is dl by dx dot is just mx dot. So that's just my momentum in the x direction times dx by dA. That's just 1. I find that my conserved quantity is momentum in the x direction. What this says is because there's no difference between me picking my origin here or my origin over here, I end up with conserved momentum in my system. That's a really powerful statement. So more generally, if my potential energy is invariant as I change x to x plus zeta for all zeta, then we know that x going to x plus zeta is a continuous symmetry of the Lagrangian. That implies that du by d zeta is equal to 0, because obviously this does not depend on whether or not I have a zeta in it. So what does that tell us? So du by d zeta is equal to 0. That tells us that we are force-free in the x direction, because here we're looking at x plus zeta. So this is a mathematical way of saying that if there are no forces some direction, say x, then the momentum in that direction is conserved. And that just comes out of the formalism of Lagrangian mechanics. We can do the same thing for rotational symmetry. Imagine I have some angle that's defined as theta plus alpha. Then my Lagrangian is 1/2 I theta dot squared, so this is the kinetic energy, minus some potential energy that depends on theta. If we look at dl by d theta dot, again, assuming that u depends only on theta and not on theta dot, that tells us that dl by d theta dot times d theta by d alpha is just equal to I theta dot, or I omega. This is the definition of angular momentum. Having a system that is rotationally symmetric guarantees that you will have conservation of angular momentum. It's a property of the symmetry of the system that gives us these powerful conserved quantities. In my opinion, Noether's theorem is really the most profound part of the undergraduate physics curriculum. This is one of the most powerful statements, and it applies to physics at all levels. Here we approach it from the point of view of classical mechanics, but it works in quantum mechanics, it works at general relativity. This is something that exceeds the boundaries that we set up between physics disciplines, and that's one of the reasons it's so powerful.